Okay, is my screen visible?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
Okay. So to start with, we are going to start with the fourth module, that is flexibility matrix method. First module was regarding slope deflection method. Second module was regarding moment distribution method. And the third module is regarding the Kani's method. And this fourth module is with respect to the flexibility matrix method. And the fifth module deals with the stiffness matrix method. Okay. The fourth and the fifth module deal with the matrix method of structural analysis. Now we have seen from right from module 1 up to module 3, Kani's method, we have seen how the systems have been evolved or how the procedures have been evolved. And the slope deflection method you saw a very tedious one, which was include which used to have lot of equations to be solved and everything. Then we came to the moment distribution method, a simple tabular format, which was much easier than the slope deflection method. And now you are seeing the Kani's method also, which is much more easier than the slope deflection method and the moment distribution method. Okay. So right from first module up to the third module, you have seen the evaluation of the method, how they try to make the method much more easier, and how they try to include much more complex structure, which can be solved very easily. Right? Like if you take one method, like if you take a frame structure and solve it by using a slope deflection method and solve it by using a Kani's method, you can see the difference how quickly you can do using Kani's method than the slope deflection method. Yes, after the Kani's method, they are introducing one more method called the flexibility matrix method, which is much more easier than first other three modules. Okay, and you can see the one more method, that is the stiffness matrix method, which will be much more easier than all other methods. The stiffness matrix method is the latest method which they are adopting nowadays in case of softwares also. And after that, we have finite element method and many more methods are there. So for you, your semester, the scope is only up to the stiffness matrix method. Of course, the flexibility matrix method and the stiffness matrix method, they have just introduced you people. It is not a total one. So if you want to read more about that, you have to take an elective which comes in, I think, in sixth or seventh semester. That is specially for matrix method of structural analysis. And in PG, we have a separate subject only, that is computational structural mechanics, which deals with only the matrix method of structural analysis. Okay. Uh, with this, what I will do, I will today this class I will try to explain you a simple concept behind the flexibility matrix method. Then in my next class, I will take one simple example and I will try to make you thorough with the flexibility matrix method. But there is one request from my side, that all of you please uh, glance through conjugate beam method. Okay, because I will be using conjugate beam method frequently in this module, right? So I may not be able to explain you the whole conjugate beam method once again. So I request you people to once again please go through the conjugate beam method. My videos are there, previous semester videos, or if you want, I will share my notes also. I think I have shared. I will once again share the conjugate beam method notes, or you can refer any of the textbook, or you can refer YouTube channel or whatever. Okay, please go through the conjugate beam method because that is much more important in this model, right? Okay. I will start with this thing. Now you can see here, this is a propped cantilever beam. Why we call it is a propped cantilever? Because one end is fixed and the other end is roller. Okay, it is a propped cantilever. Is it an indeterminate structure or determinate structure? Can anybody tell me? Is it a determinate structure or indeterminate structure? Yes, students, am I audible? Hello, am I audible, students? Am I audible?
Yes, sir.
Yeah. Okay. Tell me whether it is a determinate one or indeterminate structure. Hmm? Anyone? Okay. Please see if at this stage you are unable to recognize.
Indeterminate.
Yeah. How can you say
And
indeterminate? How can you say
so
indeterminate?
R is greater than 3n.
Yeah, you can see here. Very simple thing. So how many unknown reactions are there at the fixed support? So let me draw. There is a one vertical unknown reaction. Also we have a horizontal unknown reaction. Also we have a movement. Okay. Totally there are three unknown reactions here and one unknown reaction here. Okay. So the total number of unknown reactions are 4, but the number of equilibrium equations available are actually 3. So R is greater than the number of equilibrium equations. So I can call this structure as an indeterminate structure. Okay. To what degree it is indeterminate? So to you can
1.
just mention, yeah, 1, because that is 4 minus 3. That is 1. So the structure is indeterminate to first degree. Okay. So this is the basic thing what you have to see first. Right. Now after this, what I will do, I want to analyze this structure now, right? Using a matrix flexibility matrix method. Let us keep flexibility matrix method at other side. Let us see the approach, right? Now, this is the proper cantilever beam. So we have point load P exactly at the center. I can call. Okay. So because of that, the beam will deflect something like this. Okay, you can see there is no deflection or no rotation here because there is a fixed support, right? So the beam will have a deflection like this. Since there is a propped cantilever, that is the roller support at B, so there will not be any deflection at point B also. Now what I will do, I will draw the same structure. I will draw the same structure. Everything is same except one thing. What is that difference is I'm going to remove this roller support at B. Okay, same structure I have taken, same length, everything is same amount of load. Only thing is I will remove this roller support. Now what happens whether the structure is now determinate or still it is indeterminate?
Determinate.
Yeah, now it is determinate. Yeah, now it is determinate, right? Now how will be the deflection? The deflection will be something like this. Do you agree? Right?
Yes, sir.
Yeah. Now let me call say this deflection as delta B. I will call this deflection as say delta B, right? Okay. Okay. Now, now what I will do, I will draw the same beam once again. Okay. So I will mark the name numbers A, B. I will draw the same beam. Now the difference is instead of load P means I will remove that load P here. Okay. Whatever load, external load P was acting, I will remove that. Instead of that, what I will do, I will try to apply a unit load at B. I will try to apply a unit load at B. Why am I doing all these kind of things? I will explain you at the end. Okay. So in the next structure, I will remove the external load P, and at B, I'm going to apply one unit load. It could be 1 kilonewton, 1 newtons or 1 kg or whatever. Okay. One unit load I'm going to apply. Now how the beam will deflect at this point of time? At this point of time, the beam will deflect like this. Do you agree?
Yes, sir.
Yeah. Now let me call this deflection as FBB. What is that FBB? Why I'm calling this FBB? I will tell you. Let me call that as FBB. Okay, right. Once again, what I will do, I will draw the same structure. So I'm going to draw the same structure, same beam. Now also I will not put the external load. Now also I will not put the external load. Okay, now instead of unit load at B, let me apply a load by. Okay, Let me apply the load By at B. So how the beam will deflect? The beam will deflect like this. Yes, I will
Yes,
call,
sir.
yeah, I will call this deflection at this in this beam as say FBB into By. Do you agree with this? This deflection, I'm calling it as FBB into By. How it is possible is, I will tell you. See, for unit load, the deflection is FBB. So for By, it is FBB into By. Do you agree?
Yes, sir.
Yeah. Okay, I will explain once again. For unit load, the deflection is FBB. So for By load, it is FBB into By. Have you understood?
Yes, sir.
Okay, right. Now let
Yes,
me,
sir.
yeah, now let me just tell what are all these terms. Of course, this delta B is the deflection due to the point load. Okay, no need to worry about that. This FBB is actually called as flexibility coefficient. It is called as flexibility coefficient, and definition of that FBB is actually deflection at B due to unit load at B. Okay, it is deflection at B. Okay, deflection at B due to the unit load at B. That's why I'm putting a suffix as B and B. That is deflection at B due to the unit load applied at B. Okay, that's why I'm calling it as FBB. Why F? Because F actually represents flexibility coefficient. Okay, so this FBB is called flexibility coefficient, and the definition of that is deflection at B due to the unit load at B. Is it clear up to this point? Are you clear?
Yes, sir.
Yes, everyone? Everyone?
Yes, sir.
Yeah, okay. Now I will do one thing. I will just try to write few things here. Let me call this structure as say P. Okay, let me call this structure as say P, and let me call this structure as say Q. Okay, and at the end, let me call this structure as say R. Okay, now if you see PQ and R, okay, let me just keep this on the other side so that it will be very easy for you to understand. Okay. 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 Right. Now, if you see PQ and R in P structure at B, in P structure at B, there is no deflection. Yes or no? In structure P at B, there is no deflection. In structure Q at B, there is a deflection of delta B. Now in structure R at B, there is a deflection of FBB into BY. Now if I see at point B in structure P, Q and R, can I write this equation? I can write like this. P is equal to Q plus R. Okay, so in structure P at B, what is the deflection? It is 0, equal to In Q structure at B, what is the deflection? Delta B. In R structure at B, what is the deflection? FBB into BY. Do you agree with this equation?
Yes,
Yes,
sir.
sir.
Yes. Okay. Now, right. Now, when you see Q structure is a determinate structure. Yes. Okay. And this delta B deflection at B, you can find using any of the methods which you have already studied in ADS. What are the methods? You have studied double integration method, Macaulay's method, moment area method, conjugate beam method, virtual work principle method. Many methods are there to find deflection in a determinate beam. So it means that you can easily find delta B using any of the methods. Do you agree? Yes or no?
Yes, sir.
Yeah. Now, once you this structure, that is this one, that is this one. Okay. So this structure is also a determinate structure, and applying unit load at B, that is 1, you can find this FBB once again by any of the methods which you already studied. That is conjugate beam method, moment area method, or any method you can find this FBB, because this structure is still a determinate structure. So this FBB also can be found. Do you agree? Yes or no? Yes, right?
So once again,
Yeah, what let me just explain you once again. Have you understood this equation? How I wrote?
Yes,
yes,
sir.
sir.
Okay. In that case, so what are the unknown things in this equation? Delta B, FBB, and BY. Okay, right. Now, how will you find all these terms? Now, delta B is from Q structure. Delta B is the deflection at the free end of a cantilever beam, which is having a point load P exactly at the center. Simple thing. I will explain once again. Delta B is the deflection at the free end of a cantilever beam which is having a point load P exactly at the center. Now this structure is a determinate structure. This structure is a determinate structure. This delta B can be found using any of the methods which you already studied in ADS, that is analysis of determinate structure subject. That is, you have studied double integration, Macaulay's method, moment area method, conjugate beam method, virtual work principle. Many methods are there which you can use to find this delta B. So in this equation, you can easily find this delta B. Do you agree?
Yes, sir.
Yeah. Now, what is this FBB? FBB is the deflection in a cantilever beam at the free end due to the application of unit load 1 at the free end. This is also once again a determinate structure. This structure is also once again a determinate structure. Once again, you can find this FBB value using any of the methods which you have studied in ADS. So it means you can find FBB also.
Yes, sir.
Yes. Yeah. So once you know delta B and FBB, using this equation, you can easily find BY.
Yes, sir.
But what is that BY now? That BY is nothing but this one. Yes or no? This BY is nothing but the vertical reaction at the roller support B. So this is that BY. Yes or no?
Yes, sir.
Yeah, okay. So once you know this BY, the other unknowns can be easily found. Why? Because you had totally 4 unknown reactions. Out of these 4 unknown reactions, you have already found one, which is that one. That one is BY. So the what are the other three? Other three are nothing but AX, which we usually neglect, AY, and MA. These other three can be easily found by using equations of equilibrium. Is it clear now? Students, are you clear?
Yes, sir.
Yes, sir.
Yeah, any doubts are there in this? No, right?
So why you removed only roller support, sir?
Yeah, regarding this, I will tell you after explaining my next example.
Yes, sir.
Yeah, okay. So hope this example is bit clear to you. Okay, I will take one more example next, which will make you little more clear in the concept. Still, I have not started with the concept of flexibility, but this is the basic foundation to start with the flexibility matrix method. Okay, so let me draw one more beam here. So we have a continuous beam with a pin support, roller support, and a roller support, one more roller support. Okay, so this is A, B, and C. Let this beam be subjected to a uniformly distributed load of W. Okay, let this be L and L span. Right? Okay, am I audible?
Yes, sir.
Yeah,
Yes,
okay.
yes, sir.
Now, yeah, now once again, this is an indeterminate structure. So how many unknown reactions are there? Let us neglect the axial force. Okay, let me take the axial force. So how many unknown reactions are there? 1, 2, 3, and 4. So 4 unknown reactions are there, but we have only 3 equilibrium equations. So it is indeterminate to a degree of 1. Right? Okay. Now same procedure what I did in this example, the same thing I'm going to do. First, the same beam I will take. Same beam I will take. Now in my previous example, I removed the roller support which was there at B. Now in this example, I will remove this roller support. I will remove this roller support, but all other loads I will keep as it is. The load which was there earlier, I will keep as it is. The only difference is I have removed the roller support at B. So this is your point A, this is your point B, and this is your point C. Now the structure is determinate. Do you agree? Right?
Yes, sir.
Yeah. In
Yes,
this
sir.
in this indeterminate structure, if this was the loading, the deflection would have been something like this. Something like this. Now the deflection is like this. Yes. Okay. Let me call this deflection as say delta B. Okay. Let me call this deflection as say delta B. Now once again, what I will do, I will draw the beam, same beam without the roller support at B and without the external load W. But now at B, I will introduce a unit load. At B, I will introduce a unit load. So this is A, this is B, this is C. Once again, it is a determinate structure. How will be the deflection? The deflection will be something like this. Okay, so this deflection, which is at B, I will call that as FBB. Okay, same thing I did no here also in the previous example. First I removed that roller support, That deflection at B, I called it as delta B. Then in my next structure, I removed the external load P. At B, I introduced a unit load. Here it is. I introduced a unit load at B and I called that deflection as FBB. Same thing I'm doing here also. I will draw one more structure. One more structure. Once again, without the roller support at B, but now at B, instead of 1, I will put a load say By. A load say By. So this is A, B, and C. Still it is a determinate structure. So how will be the deflection? Deflection will be something like this. Now what should be this deflection? Can anybody tell me?
FBB into BY.
FBB into BY.
Yes, simple. FBB into By. Because for 1 it is FBB. So for By it is FBB into By. Have you understood these 4 figures?
Yes, sir. Yes, sir.
Okay, same thing. I will call this structure as say P. This structure a Q and this structure as say R. Let me keep this structure on the other side. OK. And this structure on top of this. Yeah, now if you see, it is little clumsy. So OK. Now if you see these 3 structure P, Q and R. Now in structure P at point B, we have 0 deflection. Yes or no? There is no deflection at point B in structure P. OK. In structure Q at the same point, we have deflection of delta B. Now in structure R at the same point, that is at B, the deflection is FBB into BY. So if I try to write like this, P is equal to Q plus R. Now in structure P at point B, the deflection is 0 equal to in structure Q at point B, the deflection is delta B. In structure R at point B, the deflection is FBB into BY. Now only thing is we are actually required to find BY. So delta B is the deflection at B in structure Q. So the structure Q is a determinate one. You can find the delta B value. Many methods are there, which I told you already. Now in structure R, sorry, in this structure, not structure R. In this structure is also a determinate structure. You can find this value of FBB using many methods are there, which I already told you. So it means delta B also can be found, FBB also can be found. So in this equation, the only unknown which remains is BY, which you can find very easily. Once you find the value of BY, which is nothing but this one in structure P. This is the BY value, which is in structure P. So once you know BY, it means out of 4 unknowns, you have already found one. Only remaining are 3, which you can easily find using equations of equilibrium, by which you are able to solve this indeterminate ECP. Are you clear?
Yes, sir.
Yes, is
Yes,
it clear?
sir.
OK, right. So this is the basic or gist behind the flexibility matrix method. Right. What I will do next is we have one equation for flexibility matrix method. I will just write that equation and let me try to explain that equation using the numerical examples in my next class.
Sir.
Yeah, okay. Yeah.
So here also you removed roller support at the middle.
Okay, okay. I forgot what to answer your question. Okay. See, in structure 1, I removed the roller support at B. Okay. In structure 2 also, I removed the roller support at B. Okay. Removing these supports, okay, they are actually called as redundants. They are actually called as redundants. Choosing a redundant. Okay, how many redundants need to be chosen? That depends on the degree of static indeterminacy. In structure 1, we had only 1 degree of static indeterminacy. That is, it was indeterminate to only 1 degree. So you are supposed to choose only one redundant. In structure B also, the structure was indeterminate to first degree. So here also you have to choose only one redundant. So in structure 1, I chose roller support at B, or I can say the vertical reaction at B as the redundant. In structure 2 also, I chose the vertical reaction at B as the redundant. So you have a choice of choosing any redundant. Am I clear? You have a choice of choosing any one redundant. Here in this, I chose redundant, that is reaction at B, vertical reaction at B as the redundant. You can do that. What could be the other redundant? Can anybody tell me? In this structure only, what could be the another redundant which can be removed? Instead of reaction at B as the redundant, I want to choose one more redundant. Which could be that? Can anybody? See, totally 4 unknown reactions there. Out of these 4 unknown reactions, you can take any one as a redundant. So which is the appropriate one? Can anybody? I don't want to remove by. I want to remove one more another redundant. Which could be the appropriate one?
So AY.
AY, not an appropriate one. Okay, you can go ahead with that, but not an appropriate one. So only left are
Sorry,
this,
AX.
this and this. Okay, AX is also not an appropriate one because we usually neglect the axial forces in the beam. So the appropriate one is this MA. Okay, now if I choose MA as the redundant, how will be that support? What could be the support that means how that fixed support becomes? If I choose MA as
Hinge.
redundant, yes, perfect.
Hinge
If I remove,
support.
yeah, if I remove MA as a redundant, fixed becomes pinned. That's it. Yes. Okay. Fixed becomes
Yes,
pinned.
sir.
So instead of this fixed support, I should write here the pinned support. Okay. And this roller support B will be there as usual. Do you agree? Right? So if you are unable to
Yes, sir.
understand, please just keep this in mind. So we'll solve many more numerical examples. At that point of time, you will understand. Now in this structure, can anybody tell me? This is very easy. Can anybody tell me what are the other redundants possible to be removed instead of BY?
X.
AX you neglect. What are the other two possibilities?
So at C.
At C,
C.
that is CY and AY. Yes or no?
Yes, sir.
Okay, if I remove CY, how will be the structure? The structure becomes something like this. So this will be as it is. So a BM I'm not removing. So this will be there. So CY I'm removing. So the structure becomes like this. So this is a determinate or indeterminate? This structure,
Determinate.
yeah, determinate. Now if I,
Determinate.
yeah, now if I remove AY, how will be the structure? So this roller will be as it is. This roller will be as it is. Nothing will be there here. Still it is a determinate one. Actually this is not a determinate, it is an unstable one. Okay, because 2 rollers are there. So actually it is an unstable one. So this is not a correct option. So removing CY is could be the correct option instead of BY. Right? But what happens? See, if you remove CY, there is a uniformly distributed load. How will be the deflection? The deflection could be something like this. Okay, so finding this deflection using any other method could be a tedious one. Okay, but if you remove by, so we have a direct standard formula to find the delta b and all. So usually you have to choose the redundant very carefully so that your calculations becomes very easy for you. Are you clear?
Yes, sir.
Yeah. Now
Yes,
in
sir.
now in these two structures, we had only one redundant. But what if there are many redundants? Maybe something like this. I will give you an example. This is a fixed support. This is a roller support. This is a roller support. Okay, what is the statical indeterminacy of this structure? So how many reactions are there? 1, 2, and 3 plus 1 plus 1. Okay, so 3 plus 2, 5. 5. How many equilibrium equations? 3. So how many redundants need to be chosen? 2 redundants. Okay, it depends on you which two you will choose. I can choose these two as the redundants. Are you clear?
Yes, sir.
Yeah, we'll see such type of problems in the future. But now at the final, I want to give one equation called as flexibility matrix equation. So I will explain you what is all these things. Okay, so this equation is actually called as an flexibility matrix equation. Now what is the meaning of each and every term? I will explain. This is called flexibility matrix. Flexibility matrix. Okay, this is called vector redundant matrix, and this is called vector displacement matrix. Okay, now what is all these things I will tell you. First, let me explain you why I have put a square bracket. Square bracket, it means the matrix is a square matrix. Okay, what is the meaning of square matrix? Can anybody?
Number of rows is equal to
Rows are
columns.
equal.
Yes. Square matrix is a one where number of rows is equal to number of columns. Now, if I put a flower bracket, what is the meaning of that?
They are not equal.
No, it is not like that. Flower bracket, it means it is a column vector, means matrix will be having only elements in the column form. Okay, only one column will be there, right? Here also flower bracket, it means only one column of matrix will be there, right? Okay, if we have many redundants, okay, so the matrix becomes something like this. So this flexibility matrix contains F11, F12 up to F1n, whatever, how many numbers are there. So this becomes F21, F22, F2n. So this becomes Fn1, Fn2, Fnn. Okay. This redundant matrix includes R1, R2 up to Rn. How many numbers are there? That many numbers. Okay, equal to this displacement matrix includes delta 1, delta 2, delta n. Right? So in this, usually we are able to find the flexibility matrix, means this matrix will be known to us and this matrix will also be known to us. Okay, the only unknown matrix which will be there is this one, which we can easily find. Means if I take this matrix on this side, I have to make a inverse, and I can find this matrix, or you can do cross multiplication and simultaneous equations can be formed and you can find the unknowns. So using how to use this matrix and all, I will explain you in my next class when we take up a simple numerical examples. Are you clear?
Yes, sir.
Right. So
Yes,
this
sir.
is, yeah, this is the gist or the main foundation behind the flexibility matrix method. So I will stop my class here. In my next class, I will take up one simple numerical example to make you understand how we can use the flexibility matrix method. Okay, but once again, I'm telling you one and all, please once again read the conjugate beam method, which you have already studied in your ADS, right? Because that I'm going to use frequently. Are you clear? Any doubts you have?